It's the difference between X and Y when you draw axes on a piece of paper.
So there's really no difference.
There's almost no difference. There's one difference that is kind of important, which is the following. If you have a curve in space, I'm going to draw it horizontally because that's usually what we do in space-time diagrams. If you have a curve in space, you've heard the motto before that the shortest distance between 2 points is a straight line. If you have a curve in time, which is, by the way, literally all of our lives, right? We all evolve in time. So you can start with one event in space-time and another event in space-time. What Minkowski points out is that the time you measure along your trajectory in the universe is precisely analogous to the distance you travel on a curve through space. And by precisely, I mean it is also true that the actual distance you travel through depends on your path, right? You can go a straight line, shortest distance, you can curvy line to be longer. The time you measure in space-time, the literal time that ticks off on your clock, also depends on your path. But it depends on it the other way. So that the longest time between 2 points is a straight line. And if you zig back and forth in space-time, you take less and less time to go from point A to point B.
How do we make sense of that? The difference between the observed reality and the objective reality underneath it? Or is objective reality a silly notion given general relativity?
I'm a huge believer in objective reality. I think that objective reality
You're a
objectively
fan.
is real.
Yeah.
But I do think that people kind of are a little overly casual about the relationship between what we observe and objective reality in the following sense. Of course, in order to explain the world, our starting point and our ending point is our observations, our experimental input, the phenomena we experience and see. Time between 2 points is a straight line. And if you zig back and forth in space-time, you take less and less time to go from point A to point B.
How do we make sense of that? The difference between the observed reality and the objective reality underneath it? Or is objective reality a silly notion given general relativity?
I'm a huge believer in objective reality. I think that objective reality
You're a
objectively
fan.
is real.
Yeah.
But I do think that people kind of are a little overly casual about the relationship between what we observe and objective reality in the following sense. Of course, in order to explain the world, our starting point and our ending point is our observations, our experimental input, the phenomena we experience and see around us in the world. But in between, there's a theory. There's a mathematical formalization of our ideas about what is going on. And if a theory fits the data and is very simple and makes sense in its own terms, then we say that the theory is right. And that means that we should attribute some reality to the entities that play an important role in that theory, at least provisionally until we come up with a better theory down the road.
I think a nice way to test the difference between objective reality and the observed reality is what happens at the edge of the horizon of a black hole. So technically, as you get closer to that horizon, time stands still.
Yes and no. It
Okay.
depends on exactly how careful we're being. So here is a bunch of things I think are correct. If you imagine there is a black hole space-time, so like the whole solution to Einstein's equation, and you treat you and me as what we call test particles. So we don't have any gravitational fields ourselves. We just move around in the gravitational field. And that's obviously an approximation, okay? But let's imagine that. And you stand outside the black hole and I fall in, and as I'm falling in, I'm waving to you, because I'm going into the black hole, you will see me move more and more slowly. And also the light from me is redshifted, so I kind of look embarrassed because I'm falling into a black hole. And there is a limit. There's a last moment that light will be emitted from me, from your perspective, forever. Okay? Now, you don't literally see it because I'm emitting photons more and more slowly, right? Because from your point of view. So it's not like I'm equally bright. I basically fade from view in that picture. Okay, so that's one approximation. The other approximation is I do have a gravitational field. of my own. And therefore, as I approach the black hole doesn't just sit there and let me pass through, it kind of moves out to eat me up
Hmm.
because its net energy mass is going to be mine plus its. But roughly speaking, yes, I think so. I don't like to go to the dramatic extremes because that's where the approximations break down. But if you see something falling into a black hole, you see its clock ticking more and more slowly.
How do we know it fell in?
We don't. I
Huh.
mean, how would we? Because it's always possible that right at the last minute it had a change of heart and starts accelerating away, right? If you don't see it pass in, you don't know. And let's point out that as smart as Einstein was, he never figured out black holes, and he could have. It's kind of embarrassing. It took decades for people thinking about general relativity to understand that there are such things as black holes, because basically Einstein comes up with general relativity in 1915. 2 years later, Carl Schwarzschild, derives the solution to Einstein's equation that represents a black hole, the Schwarzschild solution. No one recognized it for what it was until the 50s, David Finkelstein and other people. And that's just, one of these examples of physicists not being as clever as they should have been.
Well, that's the singularity. That's the kind of the edge of the theory, the limit. So it's understandable that it's difficult to imagine the limit of things.
It is absolutely hard to imagine, and a black hole is very different in many ways from what we're used to. On the other hand, the real reason, of course, is that between 1915 and 1955, there's a bunch of other things that are really interesting going on in physics, all of particle physics and quantum field theory. So many of the greatest minds were focused on that. But still, if the universe hands you a solution to general relativity in terms of curved spacetime and it's kind of mysterious, certain features of it, I would put some effort into trying to figure it out.
So how does a black hole work? Put yourself in the shoes of Einstein and take general relativity to its natural conclusion about these massive things.
It's best to think of a black hole as not an object so much as a region of space time. Okay. It's a region with the property, at least in classical general relativity. Quantum mechanics makes everything harder, but let's imagine we're being classical for the moment. It's a region of space time with the property that if you enter, you can't leave. Literally, the equivalent of escaping a black hole would be moving faster than the speed of light. They're both precisely equally difficult. You would have to move faster than the speed of light to escape from the black hole. So once you're in, that's fine. In principle, you don't even notice when you cross the event horizon, as we call it. The event horizon is that point of no return, where once you're inside, you can't leave. But meanwhile, the space time is sort of collapsing around you to ultimately a singularity in your future, which means that the gravitational forces are so strong they tear your body apart, and you will die in a finite amount of time. The time it takes, if the black hole is about the mass of the sun, to go from the event horizon to the singularity takes about 1 millionth of a second.
Mhm. And what happens to you if you fall into the black hole? Like, if we think of an object as information, that information gets destroyed.
Well, you've raised a crucially difficult point.
Mm.
So that's why I keep needing to distinguish between black holes according to Einstein's theory of general relativity, which is book one of Spacetime and Geometry, which is perfectly classical. And then come the 1970s, we start asking about quantum mechanics and what happens in quantum mechanics. According to classical general relativity, the information that makes up you when you fall into the black hole is lost to the outside world. It's there, it's inside the black hole, but we can't get it anymore. In the 1970s, Stephen Hawking comes along and points out that black holes radiate. They give off photons and other particles to the universe around them. And as they radiate, they lose mass and eventually they evaporate, they disappear. So once that happens, I can no longer say the information about you or a book that I threw in the black hole or whatever is still there, it's hidden behind the black hole because the black hole has gone away. So either that information is destroyed, like you said, or it is somehow transferred to the radiation that is coming out, to the Hawking radiation. The large majority of people who think about this believe that the information is somehow transferred to the radiation and information is conserved. That is a feature both of general relativity by itself and of quantum mechanics by itself. So when you put them together, that should still be a feature. We don't know that for sure. There are people who have doubted it, including Stephen Hawking for a long time. But That's what most people think. And so, what we're trying to do now in a topic which has generated many, many hundreds of papers called the black hole information loss puzzle is figure out how to get the information from you or the book into the radiation that is escaping the black hole.
Is there any way to observe Hawking radiation to a degree where you can start getting insight, or is this all just in the space of theory right now?
Right now, we are nowhere close to observing Hawking radiation. Here's the sad fact: the larger the black hole is, the lower its temperature is. So, a small black hole, like a microscopically small black hole, might be very visible. It's given off light. But something like the black hole at the center of our galaxy, 3 million times the mass of the sun or something like that, Sagittarius A star, that is so cold and low temperature that its radiation will never be observable. Black holes are hard to make. We don't have any nearby. The ones we have out there in the universe are very, very faint. So there's no immediate hope for detecting Hawking radiation.
Allegedly, we don't have any nearby.
As far as we know, we don't have any nearby.
Could tiny ones be hard to detect? Somewhere at the edges
Absolutely.
of the solar system, maybe?
So you don't want them to be too tiny or they're exploding, right? Or they're very bright and then they would be visible. But there's an absolutely a regime where black holes are large enough not to be visible because the larger ones are fainter, right? Not giving off radiation, but small enough to not been detected through their gravitational effect. Yeah.
Psychologically, just emotionally, how do you feel about black holes? They scare you?
I love them. I love black holes, but the universe weirdly makes it hard to make a black hole,
Mhm.
right? Because you really need to squeeze an enormous amount of matter and energy into a very, very small region of space. So we know how to make stellar black holes. A supermassive star can collapse to make a black hole. We know we also have these supermassive black holes at the center of galaxies. We're a little unclear where they came from. I mean, maybe stellar black holes that got together and combined. But that's one of the exciting things about new data from the James Webb Space Telescope is that quite large black holes seem to exist relatively early in the history of the universe. So it was already difficult to figure out where they came from. Now it's an even tougher puzzle.
So these supermassive black holes are formed somewhere early on in the universe. I mean, that's a feature, not a bug, right? That we don't have too many of them. Otherwise, we wouldn't have the time or the space to form the little pockets of complexity that we call humans.
I think that's fair. Yeah. It's always interesting when something is difficult but happens anyway, right? I mean, the probability of making a black hole could have been zero, it could have been one, but it's this interesting number in between, which is kind of fun.
Are there more intelligent alien civilization than there are supermassive black holes?
Yeah, I have no idea,
I was
but I
hoping
think
you would.
your intuition is right that it would have been easy for there to be lots of civilizations and then we would have noticed them already. And we haven't. So, absolutely, the simplest explanation for why we haven't is that they're not there.
Yeah, I just think it's so easy to make them, though. So there must be. I understand that's the simplest explanation, but
How
also
easy is it to make life or
it
eukaryotic
just
life or multicellular life?
it seems like life finds a way. Intelligent alien civilizations, sure, maybe there is somewhere along that chain a really, really hard leap. But once you start life, once you get the origin of life, it seems like life just finds a way everywhere in every condition. It just figures it out.
I mean, I get it. I get exactly what you're thinking. I think it's a perfectly reasonable attitude to have before you confront the data. I would not have expected Earth to be special in any way. I would have expected there to be plenty of very noticeable extraterrestrial civilizations out there. Um, but even if life finds a way, even if we buy everything you say, how long does it take for life to find a way? What if it typically takes 100 billion years? Then we'd be alone.
So it's a time thing. So to you, really, there's most likely there's no alien civilizations out there. I can't see it. I believe there's a
Yeah,
ton of them, and there's another explanation why we can't see them.
I don't believe that very strongly. Look, I'm not going to place a lot of bets here. I would not. I'm both pretty up in the air about whether or not life itself is all over the place. It's possible when we visit other worlds, other solar systems, there's very tiny microscopic life ubiquitous, but none of it has reached some complex form. It's also possible there's just There isn't any. It's also possible that there are intelligent civilizations that have better things to do than knock on our doors. So I think we should be very humble about these things we know so little about.
And it's also possible there's a great filter where there's something
See
fundamental
around us in
about
the world. But
uh,
in between,
once a civilization develops complex of technology, that technology is more.
Hmm, there's a theory. There's a mathematical formalization.
Definitely pre-order it. It's titled Quanta. Definitely pre-order it. It's titled Quanta and Fields, and that one is on the topic of quantum mechanics.
Have in a region of space-time. It's what heaven is that they're not there. Following sense. Of course, in order to explain the world, our starting point and our ending point is our observations, our experimental input, the phenomena we experience and see around us in the world. But in between, there's a theory. There's a mathematical formalization of our ideas about what is going on. And if a theory fits the data and is very simple and makes sense in its own terms, then we say that the theory is right. And that means that we should attribute some reality to the entities that play an important role in that theory, at least provisionally until we come up with a better theory down the road.
I think a nice way to test the difference between objective reality and the observed reality is what happens at the edge of the horizon of a black hole. So technically, as you get closer to that horizon, time stands still.
Yes and no. It
Okay.
depends on exactly how careful we're being. So here is a bunch of things I think are correct. If you imagine there is a black hole space-time, so like the whole solution to Einstein's equation, and you treat you and me as what we call test particles. So we don't have any gravitational fields ourselves. We just move around in the gravitational field. And that's obviously an approximation, okay? But let's imagine that. And you stand outside the black hole and I fall in, and as I'm falling in, I'm waving to you, because I'm going into the black hole, you will see me move more and more slowly. And also the light from me is redshifted, so I kind of look embarrassed because I'm falling into a black hole. And there is a limit. There's a last moment that light will be emitted from me from your perspective. There to be lots of civilizations, and then we would have noticed them already. And we haven't. So absolutely the simplest explanation for why we haven't is that they're not there.
Yeah, I just think it's so easy to make them, though. So there must be. I understand that's the simplest explanation, but
How
also
easy is it to make life, or
it
eukaryotic
just
life, or multicellular life?
it seems like life finds a way. Intelligent alien civilizations, sure, maybe there is somewhere along that chain a really, really hard leap. But once you start life, once you get the origin of life, it seems like life just finds a way everywhere in every condition. It just figures it out.
I mean, I get it. I get exactly what you're thinking. I think it's a perfectly reasonable attitude to have before you confront the data. I would not have expected Earth to be special in any way. I would have expected there to be plenty of very noticeable extraterrestrial civilizations out there. But even if life finds a way, even if we buy everything you say, how long does it take for life to find a way? What if it typically takes 100 billion years? Then we'd be alone.
So it's a time thing. So to you, really, there's most likely there's no alien civilizations out there. I can't see it. I believe there's a
Yeah,
ton of them, and there's another explanation why we can't see them.
I don't believe that very strongly. Look, I'm not going to place a lot of bets here. I would not. I'm both pretty up in the air about whether or not life itself is all over the place. It's possible when we visit other worlds, other solar systems, there's very tiny microscopic life ubiquitous, but none of it has reached some complex form. It's also possible there isn't any. It's also possible that there are intelligent civilizations that have better things to do than knock on our doors. So I think we should be very humble about these things we know so little about.
And it's also possible there's a great filter where there's something fundamental about uh, once a civilization develops complex enough technology, that technology is more statistically likely to destroy everybody versus to continue being creative.
That is absolutely possible. I'm actually putting less credence on that one just because you need it to happen every single time, right?
Mhm.
If even one, I mean, this goes back to John von Neumann pointed out that you don't need to send the aliens around the galaxy. You can build self reproducing probes and send them around the galaxy. And you might think, well, the galaxy is very big. It's really not. It's some tens of thousands of light years across and billions of years old. So you don't need to move at a high fraction the speed of light to fill the galaxy.
So if you were an intelligent alien civilization, the dictator of one, you would just send out a lot of probes, self-replicating probes.
100%.
Yeah,
And
just spread out.
yes, and what you should do, this is so if you want the optimistic spin, here's the optimistic spin. People looking for intelligent life elsewhere often tune in with their radio telescopes, right? At least we did before Arecibo was decommissioned. That's not a very promising way to find intelligent life elsewhere, because why in the world would a super intelligent alien civilization waste all of its energy by beaming it in random directions into the sky? For one thing, it just passes you by, right? So if we're here on Earth, we've only been listening to radio waves for 100 or a couple hundred years, okay? So if an intelligent alien civilization exists for a billion years, they have to pinpoint exactly the right time to send us this signal. It is much, much more efficient to send probes and to park, to go to the other solar systems, just sit there and wait for an intelligent civilization to arise in that solar system. This is kind of the 2001 monolith
Mhm.
hypothesis, right? I would be less surprised to find a sort of quiescent alien artifact in our solar system than I would to catch a radio signal from an intelligent civilization.
So you're a sucker for in-person conversations versus remote.
I just want to integrate over time.
Mm-hmm.
A
Integrative.
probe can just sit there and wait, whereas a radio wave goes right by you.
Mm. How hard is it for an alien civilization? Again, you're the dictator of one to figure out a probe that is most likely to find a common language with whatever it finds.
Couldn't I be like the elected leader of the
Elected
alien
leader, democratic leader,
civilization?
elected leader of a democratic alien civilization. Yes.
I think we would figure out that language thing pretty quickly. I mean, maybe not as quickly as we do when different human tribes find each other, because obviously there's a lot of commonalities in humanity, but there is logic and math, and there is the physical world. You can point to a rock and go, rock,
Mhm.
right? I don't think it would take that long. I know that Arrival, the movie, based on a Ted Chiang story, suggested that the way that aliens communicate is going to be fundamentally different. But also, they had precognition and other things I don't believe in. So I think that if we actually find aliens, that will not be our long term problem.
So there's a folks one of the places you're affiliated with is Santa Fe, and they approach the question of complexity in many different ways,
Mhm.
and ask the question in many different ways of what is life, thinking broadly. So do you would be able to find it? You'll think you show up, a probe shows up to a planet, we'll see a thing and be like, yeah, that's a living thing.
Well, again, if it's intelligent and technologically advanced, the more short term question of if we get some spectroscopic data from an exoplanet, so we know a little bit about what is in its atmosphere. How can we judge whether or not that atmosphere is giving us a signature of life existing?
Hmm.
That's a very hard question that people are debating about. I mean, one very simple minded, but perhaps interesting approach is to say small molecules don't tell you anything, because even if life could make them, something else could also make them. But long molecules, that's the kind of thing that life would produce.
So signs of complexity.
Hmm.
I don't know. I just have this nervous feeling that we won't be able to detect it. We'll show up to a planet, there'll be a bunch of liquid on it. We like we take a swim in the liquid, and we won't be able to see the intelligence in it. Whether that intelligence looks like something like ants, or
Mm.
we'll see movement
Hmm.
perhaps, strange movement, but we won't be able to see the intelligence in it or communicate with it. I guess if we have nearly infinite amount of time to play with different ideas, we might be able to.
I'm in favor of this kind of humility, this intellectual humility that we won't know because we should be prepared for surprises. But I do always keep coming back to the idea that we all live in the same physical universe. And if, well, let's put it this way. The development of our intelligence has certainly been connected to our ability to manipulate the physical world around us. And so I would guess, without 100% credence by any means, but my guess would be that any advanced kind of life would also have that capability. Both dolphins and octopuses are potential counterexamples to that. But I think in the details, there would be enough similarities that we would recognize it.
I don't know how we got on this topic, but I think it was from supermassive black holes. So if we return to black holes and talk about the holographic principle more broadly,
Mm.
you have a recent paper on the topic. You've been thinking about the topic in terms of rigorous research perspective and just as a popular book writer.
Hmm.
So what is the holographic principle?
Well, it goes back to this question that we were talking about with the information and how it gets out. In quantum mechanics, certainly, arguably even before quantum mechanics comes along in classical statistical mechanics, there's a relationship between information and entropy. Entropy is my favorite thing to talk about, that I've written books about and will continue to write books about. So Hawking tells us that black holes have entropy. And it's a finite amount of entropy. It's not an infinite amount. But the belief is, and now we're already getting quite speculative, the belief is that the entropy of a black hole is the largest amount of entropy that you can have in a region of spacetime. It's sort of the most densely packed that entropy can be. And what that means is there's sort of a maximum amount of information that you can fit into that region of space, and you call it a black hole. And interestingly, you might expect if I have a box and I'm going to put information in it, and I don't tell you how I'm going to put the information in, but I ask, how does the information I can put in scale with the size of the box? You might think, well, it goes as the volume of the box because the information takes up some volume and I can only fit in a certain amount. And that is what you might guess for the black hole, but it's not what the answer is. The answer is that the maximum information, as reflected in the black hole entropy, scales as the area of the black hole's event horizon, not the volume inside. So people thought about that in both deep and superficial ways for a long time, and they proposed what we now call the holographic principle, that the way that space time and quantum gravity convey information or hold information is not different bits or qubits for quantum information at every point in space time. It is something holographic, which means it's sort of embedded in or located in or can be thought of as pertaining to one dimension less of the three dimensions of space that we live in. So in the case of the black hole, the event horizon is two-dimensional, embedded in a three-dimensional universe. And the holographic principle would say all of the information contained in the black hole can be thought of as living on the event horizon rather than in the interior of the black hole. I need to say one more thing about that, which is that this was an idea. What the idea I just told you was the original holographic principle put forward by people like Gerard de Tooft and Leonard Susskind, super famous physicist. Leonard Susskind was on my podcast and gave a great talk. He's very, very good at explaining these things.
Mindscape podcast.
Mindscape
Everybody should listen.
podcast. That's right. Yes.
And you don't just have physicists on.
I don't.
I love Mindscape.
Oh, thank you very much.
Curiosity driven.
Yeah, ideas.
Exploration
Big
of ideas.
from smart
Yeah.
people. Yeah. But anyway, what I was trying to get at was Susskind and also at Tufte were a little vague. They were a little hand wavy about holography and what it meant. Where holography, the idea that information is sort of encoded on a boundary, really came into its own was with Juan Maldacena in the 1990s. And the ADS CFD correspondence, which we don't have to get into any detail, but it's a whole full-blown theory of, it's two different theories. One theory in n dimensions of space-time without gravity, and another theory in n+1 dimensions of space-time with gravity. And the idea is that this n-dimensional theory is, casting a hologram into the n+1 dimensional universe to make it look like it has gravity. And that's holography with a vengeance. And that's an enormous source of interest for theoretical physicists these days.
How should we picture what impact that has? The fact that you can store all the information you can think of as all the information that goes into a black hole can be stored at the event horizon.
Yeah, I mean, it's a good question. One of the things that quantum field theory indirectly suggests is that there's not that much information in you and me compared to the volume of space time we take up. As far as quantum field theory is concerned, you and I are mostly empty space. And so we are not information dense, right? The density of information in us or in a book or a CD or whatever, computer RAM, is indeed encoded by volume. Like there's different bits located at different points in space, but that density of information is super duper low. So we're just like the speed of light or just like the Big Bang. For the information in a black hole, we are far away in our everyday experience from the regime where these questions become relevant. So it's very far away from our intuition. We don't really know how to think about these things. We can do the math, but we don't feel it in our bones.
So you can just write off that weird stuff happens in a
Well, we'd
black
like to
hole.
do better, but we're trying. I mean, that's why we have an information loss puzzle, because we haven't completely solved it. So here's just one thing to keep in mind. Once space-time becomes flexible,
Mhm.
which it does according to general relativity, and you have quantum mechanics, which has fluctuations in virtual particles and things like that, the very idea of a location in space-time becomes a little bit fuzzy, right? Because it's flexible and quantum mechanics says you can't even pin it down. So information can propagate in ways that you might not have expected. And that's easy to say, and it's true, but we haven't yet come up with the right way to talk about it that is perfectly rigorous.
But it's crazy how dense with information a black hole is, and then plus like quantum mechanics starts to come into play. So you almost want to romanticize the kind of interesting computation type things that are going on inside the black hole.
You do, but I'll point out one other thing. It's information dense, but it's also very, very high entropy. So a black hole is kind of like a very, very, very specific random number, right? It takes a lot of digits to specify it, but the digits don't tell you anything. They don't give you anything useful to work on. So it takes a lot of information, but it's not of a form that we can learn a lot from.
But hypothetically, I guess as you mentioned, the information might be preserved. The information that goes into a black hole, it doesn't get destroyed. So what does that mean when the entropy is really high?
Well, the black hole, I said that the black hole is the highest density of
Right.
information, but it's not the highest amount of information because the black hole can evaporate. And when it evaporates, and people have done the equations for this, when it evaporates, the entropy that it turns into is actually higher than the entropy of the black hole was, which is good because entropy is supposed to go up. But it's much more dilute, right? It's spread across a huge volume of space time. So, in principle, all that you made the black hole out of, the information that it took, is still there, we think, in that information, but it's scattered to the four winds.
We just talked about the event horizon of a black hole. What's on the inside? What's at the center of it?
No one's been there.
I
So,
came back to
again,
tell.
this is a theoretical prediction. But, I'll say one super crucial feature of the black holes that we know and love, the kind that Schwarzschild first invented. There's a singularity, but it's not at the middle of the black hole. Remember, space and time are parts of parts of one unified space-time. The location of the singularity in the black hole is not the middle of space, but our future. It is a moment of time. It is like a big crunch. The Big Bang was an expansion from a singularity in the past. Big crunch probably doesn't exist, but if it did, it would be a collapse to a singularity in the future. That's what the interiors of black holes are like. You can be fine in the interior, but things are becoming more and more crowded. Space time is becoming more and more warped, and eventually you hit a limit, and that's the singularity in your future.
I wonder what time is like on the inside of a black hole.
Time always ticks by at 1 second per second. That's all it can ever do.
Yeah.
Time can tick by differently for different people. And so you have things like the twin paradox, where two people initially are the same age, one goes off near the speed of light and comes back. Now they're not. You can even work out that the one who goes out and comes back will be younger because they did not take the shortest distance path. But locally, as far as you and your wristwatch are concerned, time is not funny. Your neurological signals in your brain and your heartbeat and your wristwatch, whatever's happening to them, is happening to all of them at the same time. So time always seems to be ticking along at the same rate.
But if you fall into a black hole and then I'm an observer just watching it, and then you come out once it evaporates 1,000,000 years later, I guess you'd be exactly the same age. Have you aged at all?
You would be converted into photons. You would not be you anymore.
Right. So it's not at all possible that information is preserved exactly as it went in.
It depends on what you mean by preserved. It's there in the microscopic configuration of the universe. It's exactly as if I took a regular book, made of paper, and I burned it. The laws of physics say that all the information in the book is still there in the heat and light and ashes. You're never going to get it.
Yeah.
It's a matter of practice, but in principle, it's still there.
But what about the age of things from the observer perspective, from outside the black hole?
From outside the black hole, doesn't matter because they're inside the black hole.
No, so but isn't there okay? There's no way to escape the black hole,
Right.
except
To let it evaporate.
to let it evaporate.
But also, by the way, just in relativity, special relativity, forget about general relativity. It's enormously tempting to say, okay, here's what's happening to me right now. I want to know what's happening far away right now. The whole point of relativity is to say there's no such thing as right now when you're far away. And that is doubly true for what's inside a black hole. So you're tempted to say, well, how fast is their clock ticking? Or how old are they now? Not allowed to say that according to relativity.
Because space and time are treated the same, and so it doesn't even make sense.
That's
What happens to time in the holographic principle?
As far as we know, nothing dramatic happens. We're not anywhere close to being confident that we know what's going on here yet. So there are good unanswered questions about whether time is fundamental, whether time is emergent, whether it has something to do with quantum entanglement, whether time really exists at all. Different theories, different proponents of different things. But there's nothing specifically about holography that would make us change our opinions about time, whatever they happen to be.
But holography is fundamentally about it's a question of space.
It really is, yeah.
Okay, so time is just like a
time just goes along for the ride, as far as we know. Yeah.
So all the questions about time is just almost like separate questions, whether it's emergent and all that.
Yeah,
kind of stuff.
I mean that might be a reflection of our ignorance right now, but yes.
If we figure out a lot, millions of years from now about black holes, how surprised would you be if they travel back in time and told you everything you want to know about black holes? How much do you think there is still to know? And how mind-blowing would it be?
It does depend on what they would say. I think that there are colleagues of mine who think that we're pretty close to figuring out how information gets out of black holes, how to quantize gravity, things like that. I'm more skeptical that we are pretty close. I think that there's room for a bunch of surprises to come. So in that sense, I suspect I would be surprised. The biggest and most interesting surprise to me would be if quantum mechanics itself were somehow superseded by something